Good morning. This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. So here the topic is types of fluid flows. So let us see what is fluid flow. So fluid flow is nothing but a movement of liquids or gases. Flow, that is a movement, right? So it is very important in fluid dynamics or in fluid mechanics or in hydraulic engineering to know about the fluid flows for designing like pumps, pipelines, dams, and it is also essential for transmitting power, transmitting water, and also controlling the fluid and it to know its behavior, right? And it is also important because it allows engineers to calculate forces, to determine pipe sizes, efficient energy use in everything from small pipe to a large scale, and also in water management system. This fluid flow is very important for hydraulic engineers to calculate the forces, energy losses, to give a more efficiency uh, of flow in a pipes from small pipe to a large scale pipes, right? So here these are the classification of fluid flows. These are all the types of fluids which are classified as a steady flow, unsteady flow, uniform and non-uniform flows, one dimensional, two dimensional and three dimensional flows, rotational flows, irrotational flows, laminar flows and turbulent flows, compressible flows and incompressible flows. All these are the types of fluid flows. So here, first classification of fluid flow is a steady and unsteady flow. So the steady flow is nothing but it is a type of fluid characteristics like velocity, pressure, density, etc. are not changing at a point with respect to time is called as a steady flow. And all these fluid parameters like velocity, like pressure, like density are not at all changing with respect to time is called as a steady flow. Let the mathematical equation for the steady flow is dou v by dou t. The dou v with respect to time velocity, change in velocity or change with respect to time is not changing. That is not changing, that is constant, that is nothing but a zero, right? Dou v by dou t is equal to 0 and dou p by dou t is equal to 0 and dou p by dou t is also equal to 0 at a point in x, y, z. Dou v by dou t x naught, y naught, z naught is equal to 0. Dou p by dou t at x naught, y naught at a point at z naught is equal to 0 and density also is same. These also constant, that is not changing. These are parameters does not changing with respect to time is nothing but a steady flow, right? Steady flow, these are the variables are not changing with respect to time. This is the example for the steady flow is the flow through prismatic and non-prismatic conduct at a constant flow rate. At constant flow rate, through a prismatic or non-prismatic channel is the steady flow. Is steady flow. Prismatic channel and non-prismatic channels also we have discussed. But again I am telling you that prismatic channels are the channels which is having a definite shape. Well structure, like let us take this is your channel, right? This bottom is your bottom width b, and this is the top width T, and here is the depth of flow, let us say Y, which is having a definite shape. If it is a trapezoidal channel, then the angle which is having a definite geometry, definite shape, then that type of channels at that type of conduct, we call it as a prismatic channel. One which is having no shape, no definite dimensions, then we call it as a non-prismatic channel. Irregular shape geometry is nothing but a non-prismatic channel. This example for the non-prismatic channel is reverse. Prismatic channels is having lined canals, right? It is reverse streams. Naturally formed canals are considered as non-prismatic channels. So now unsteady flow. Unsteady flow is whatever the fluid characteristics you take, like velocity, pressure, density, at any point is changing with respect to time. Whatever the parameters you take, like velocity, pressure, density, with respect to in x direction, y direction, and in z direction, we see change with respect to time. That is here unsteady flow, right? The mathematical expression for this is dou u by dou t is equal to 0, dou v by dou t is equal to 0, sorry, is not equal to 0. Dou v by dou t is not equal to 0. It is also not equal to 0. Dou w by dou t is also not equal to 0. So the velocity which you take, here we are saying u, v, w. All these are your velocities, right? U is, if we take u, velocity u, that is in x direction. If you take velocity v, that is in y direction. If you take that w, that is in z direction. All these are velocity components. All these are velocity components, right? And so on. This pressure P with respect to time is not equal to 0. That means that is not equal to constant. And here also dou rho by dou t is not equal to 0. Not constant. Right? Not constant. So the example for this, the flow in a pipe whose value is being opened or closed gradually. Opened or closed gradually. U is equal to ax square plus bxt. This is the velocity equation for unsteady flow. Right? So here, if you take a pipe here, let us take a pipe, fluid pipe. So, this is your inlet, and here is the outlet. Here is the outlet, right? Inlet, outlet, inlet, outlet. When you take a velocity at section 1, this is the section 1. I am calculating velocity at this point at time. First I am calculating velocity at 1 second. The velocity is 1 meter per second, and after some time at 5 seconds, let us take 5 seconds, I'm calculating again velocity at this point. It is 1 meter per second. I'm calculating same at 30 seconds. At this point, the velocity is same 1 meter per second. This is the steady flow. At respective time, the velocity component is not changing. But here unsteady flow, first when you take at 1 second, it is 1 meter per second. When you take at 5 meter per second, it is 3 meter per second. And if you take here, it is 2 meter per second. Means continuously we are seeing change with respect to time velocity. Then this type of flow is your unsteady flow, right? Here is the uniform flow and non-uniform flow. So here uniform and non-uniform flows are the type of flow in which the velocity at any given time does not change with respect to space is called non-uniform flow. With respect to change, with respect to space is not uniform, right? In which the velocity at given time does not change with respect to space is non-uniform flow. That means the velocity with respect to space means lengthwise. This is the pipe flow, and we are taking section 1, section 1 1, and here is the section 2 2, right? Section 2 2. At this distance, I am calculating velocity, that is 1 meter per second, and at certain distance L, I am calculating again velocity here. The velocity is same, that is 1 meter per second, right? That means the velocity does not change with respect to space, with respect to length. That is your uniform flow. That is uniform flow. That is dou v by dou s is not changing with respect to time. That means it is constant with respect to time, with respect to space. That is nothing but your uniform flow. The value of velocity is not changing with respect to space, with respect to length is your uniform flow. Where dou v is the change in velocity, where dou s is displacement in any direction. Displacement is distance or length in any direction. Throughout it is same, that throughout it is constant, right? The example for this uniform flow is a flow through straight prismatic channel, prismatic conduct. That means that is flow through a straight pipe of constant diameter, that is through constant diameter. Non-uniform flows. Non-uniform flow, here it is a type of flow in which the velocity at any given time changes with respect to space, is changing with respect to length. With respect to length, section 1 1, the velocity is 1 meter per second. Here the velocity is 3 meter per second. We are seeing variation in the velocity in with some distance, with some length, with some space is your non-uniform flow. That is not constant. Is your non-uniform flow, right? The flow, the examples for this is flow through non-prismatic conduct, flow around a uniform diameter pipe bend or a canal bend, right? Canal bend. Now another type of fluid flow, that is one dimensional, two dimensional and three dimensional flow, right? So your one dimensional flow means name itself, it is saying that we consider the fluid parameters in only one direction, in one space coordinates, right? It is a type of flow in which the fluid flow parameters such as velocity is function of time and one space coordinates only. Velocity is a function of time and having only one space coordinate only, that is x. The u, small u, is a function of x and other v is 0 and w is 0, because where small u is a component of x direction and v is the velocity component in y direction and w is a velocity component in z direction. So these two directions are 0. We are calculating only coordinate system in in only one space coordinate system. That is your one dimensional flow. The example for this one dimensional flow is flow in a pipe where average flow parameters are considered for analysis. Average flow parameters are considered for analysis is a one dimensional flow. Two dimensional flow, right? Two dimensional flow. Here the two dimensional flow is a velocity is a function of a time and two rectangular space coordinates is called a two-dimensional flows rectangle. That is two-dimensional space coordinates, x direction and as well as in y direction. Mathematically, this as written as u is equal to f1.1 at x, y, z and v is f2 x, y, z. Right? This is x one space u and another in y space y coordinate it is v. That is two-dimensional flows. W is 0, only two coordinate system, two-dimensional flows, right? So the flow between parallel plates of infinite extent is an example of two-dimensional fluid flows, and here flow in a main pipe of a wide river is an example of two-dimensional fluid flows. Here, three-dimensional fluid flows. Three-dimensional fluid flows. That means here we are calculating the velocity components in all three mutually perpendicular directions, right? It is a type of flow in which the velocity is a function of time and three mutually perpendicular direction, that is x direction, y direction and z direction. In x direction, the velocity component is u. In y direction, the velocity component is v. And in z direction, the velocity component is a w. Right? So, mathematical equation is u is equal to f1 xyz, v is equal to f2 xyz, and w is equal to f3 xyz. This is what a mathematical expression for three-dimensional flow is. For the examples are flows in a converging, diverging pipe or a channel, and flow in a prismatic open channels in which the width and the water depth are of same order of magnitude. This is an example of three-dimensional fluid flow. Rotational and irrotational flows is another type of fluid flow. So, rotational fluid flow is a type of fluid when the fluid particles is moving in the direction of flow rotates about their mass centers is the rotational flows. A flow is said to be rotational if the fluid particles while moving in the direction of flow rotates about their mass centers. Flow near the solid boundaries is called as a rotational flows, rotational fluid flows. The example for this rotational fluid flow is motion of liquid in a rotating tank. Motion of liquid in a rotating tank is an example of rotational flows. Now, what is irrotational flows? So, irrotational flows is said to be a type of flow if the fluid particles while moving in the direction of flow does not change, does not rotate about their mass centers. The fluid particle which is moving in the direction of flow is not changing, do not rotate about their mass centers is the irrotational flows. These type of irrotational flows we see flow outside the boundary layer. We see this irrotational type outside the boundary layer. Then this outside the boundary layer is generally considered as an irrotational flows. Flow above a drain hole of a stationary tank or a wash basin. The example of this rotational flow is flow above a drain hole or a wash basin. Right? If the flow is irrotational as well as steady flow, if the flow is irrotational flow as well as steady flow, then it is known as a potential flows and it is known as a potential flows. See, here is the image of rotational flows and irrotational flows. See here, rotational flows. Here, rotational flows, the particle moves or rotates about their mass center. About rotate, mass center. But here, irrotational flows does not rotate about their mass center. Then it is irrotational flow. Right? It is irrotational flow. Rotates about the mass centers is rotational flows. The image itself, we can see what difference between the rotational and irrotational flows. Now, the main important type of fluid flow is a laminar and turbulent flows. These laminar and turbulent flows we have discussed in previous classes also. The laminar flow is a type of flow in which all the particles moves in a well defined paths or in a well defined own paths in parallel paths are in a streamlines. All the particles in a laminar flow moves in their own paths without disturbing the other particle. Let us take, if this is your pipe, the particles, these are the particles which are moving in their own paths without disturbing the other particle path. Means all particle paths are parallel and having a streamline flows, right? Parallel flow. All particles move in a laminous, in layer form, right? Individual paths in well defined paths. That is your laminar flow. That is your laminar flow. Laminar flow is one in which paths taken by the individual particle do not cross one another and move along in their well defined paths, in their own well defined paths. This type of flow is also called as streamline flows or a viscous flows. Examples of these laminar flows are flow through capillary tubes, and second example is flow in the blood in veins and arteries, and third example is groundwater flows. These are the examples of your laminar flows. Means all the particles in a laminar flow moves in their own well-defined paths, in parallel paths or in a streamlines, and it is also called as a streamline flow or also viscous flow. Here now turbulent flows. Turbulent flows is a particles are moves in a zigzag manner. Means here figure itself, here is the figure. This is the laminar and here is the turbulent flow. Laminar flow and turbulent flows, right? So here the particles, these are all the particles moving in the own paths in a straight lines, moving in without disturbing the other particles. All the particles are moving in their own paths, and this type of path is very transparent flow. We see, we can visualize also transparent flow. Flow is very smooth. All layers for smooth flows. But coming to a turbulent flows, the particle, these are all the particles are jumping from one place to another place. Particle are disturbing the other parts. This particle jumping to here, this particle here. All the zigzag flow we see here, all a zigzag flow. Why this type of flow we are seeing? Because of the velocity, because of the high velocity, because of increase in the velocity of the flow, right? This type of flow we see, and this type turbulent flow is very important flow and it is very complex to find out. And this example for the turbulent flow is high velocity flow in a conduct of large scales or large size Nearly all fluid flow problems encountered in engineering practice has a turbulent characteristics. In engineering practices, we face a main problem, that is a turbulent flows, right? Because of the high velocities flow in a large size conducts, right? See the image itself, we are seeing types of flow. See here, this is laminar, and here is the turbulent flow. Particles are disturbing one to another path, one to another. Because of this, we see energy loss is also more. Eddies formation, particle jumping from one to another path. Due to this, there is a creation of eddies formation. Because of the particle jumping from one to another path, we see high energy loss. When comparing with laminar flow, the energy loss is minimum. Energy loss is minimum. Only we see transparent. Only at the boundaries we see loss, that's it. But here, because of the particle jumping from one point to another point, we see more energy loss. And main the differentiating the laminar and turbulent flow by using a mathematical equation, that is the Reynolds number. Reynolds number is what? The Reynolds number RE is equal to inertia force by viscous force. Inertia force by viscous force. This is denoted by rho Vd by mu. Rho Vd by mu. Right? And also you are seeing another equation, that is Vd by nu. This is kinematic viscosity. And this mu is dynamic viscosity. So what is kinematic viscosity here? Let us say Re is Reynolds number, V is the velocity, and D is diameter of the pipe, and mu is dynamic viscosity. Here we are seeing kinematic viscosity. What is kinematic viscosity? Kinematic viscosity is the ratio of dynamic viscosity to density of the fluid. That is the kinematic viscosity. So in place of this mu by rho, I am writing directly nu. Another equation, R is equal to Vd by nu, kinematic viscosity. Right? By using this equation, we can differentiate the flow, laminar and turbulent flows. Right? So here is the a complete, this all thing is for pipe flow. For pipe flow, right? If the Reynolds number is less than 2000, then the flow we call as a laminar flow. If the Reynolds number is greater than 4000, then the flow is turbulent flow. If the Reynolds number is in between 2000 to 4000, then the flow is a transitional flow. This is for closed conduct, that is a pipe. Right? What about open channels? What about open channels? Open channels, if the Reynolds number is less than 5000, then the flow called as a laminar flow. Then the flow we call as a laminar flow. If the Reynolds number is greater than 2000, then the flow is turbulent flow. If the Reynolds number is in between 500 to 2000, we call it as a transitional flow. This is for open channels, and this Reynolds number is for pipe. For closed pipe, the Reynolds number is less than 2000. For open channel, the Reynolds number is less than 500. It is laminar. For turbulent in open channels, it is Reynolds number is greater than 2000. For closed conduct, greater than 4000. That is a turbulent flow. The transitional state for closed conduct is 2000 to 4000. For open channels is 500 to 2000. That is your transitional flow. See here, this is the velocity distribution diagram. Here is the velocity distribution profile. See here, all the particles moving in the own paths, but here the particles are getting disturbed, moving one to another path. See how the particles are moving in turbulent flows. But here in laminar flow, all particles are moving in their own paths, in well-defined paths. But here, when you see the particles, see here, particles are taking when flow distribution, velocity distribution in parabolic paths. Why? Because at the boundaries, at the boundaries of the pipe is having some frictional resistance. Frictional resistance. Due to this frictional resistance, the velocity at the boundary becomes minimum. At the boundaries, the velocity becomes minimum. As it will move upwards, the resistance offered by the boundary get decreased. Velocity resistance power is getting decreased. At certain point, the velocity is maximum. Whatever the velocity you are giving as an inlet, that velocity you see at the center. That is nothing but the velocity is maximum. At the center, at the boundaries, the velocity is minimum. At the center, the velocity is maximum. Velocity is minimum because of resistance offered by the boundaries, right? As the moves in upwards, as you move in y direction, the resistance power in y direction decreases. Resistance decreases. So at one point you see maximum velocity. That is at center. This is what your velocity profile for laminar flow is, parabola. Laminar flow is profile is parabola. When coming to here turbulent flow, here is a logarithmic profile. Logarithmic profile. This is what you see for turbulent flow. That is logarithmic. It is very complex problems. Right? So now is another type of flow, compressible and incompressible flows. So compressible and incompressible flows means compressible, the fluid which can compress. Incompressible, the fluid which cannot compress, right? Compressible fluids are gases, right? Air, we can compress. But water, liquids, we cannot compress, right? So compressible fluid is a type of fluid flow in which the density of the fluid changes from point to point. Density of the fluid means, let us take gases. Fluids means liquids and gases, both fluid, right? Two types. So liquid we cannot compress, incompressible, right? Incompressible. But gases we can compress. Compressible fluids is a gas. Where here the density is changing from point to point. This type of flow is called as a compressible fluids. Density is not constant throughout the flow. That fluid can be compressible fluids. The mathematically it is written as rho is not constant. That is rho is not equal to 0. Density is not equal to 0. Example, flow of gases through orifice, nozzles, gas turbines, etc. This is the example for compressible fluids. Incompressible fluids. Incompressible fluids is a type of fluid where your density is constant. Where your density is constant. That is nothing but your liquids. Liquids are generally considered as an incompressible. Water we cannot compress. So these liquids are incompressible fluids. Throughout the density of the liquid is same. The density is same. So the density is equal to 0. Density is constant. The example of this is subsonic aerodynamics. Subsonic aerodynamics. Here, ideal fluid and real fluid. Right? So, ideal fluid is nothing but directly it is an imaginary fluid. See? A fluid which is incompressible and is having no viscosity is known as an ideal fluid. Every fluid has some viscosity, but here he is saying no viscosity. Incompressible fluids and having no viscosity. That means it does not exist. It is imaginary fluid. Ideal fluid is only an imaginary fluid, right? Which does not exist. Every fluid has some viscosity, right? Ideal fluid is an imaginary fluid which does not have no viscosity, right? But here real fluid is having some viscosity, and all the fluids in practical is a real fluids. Every fluid has some viscosity, right? This is a real fluid. All practical fluids are real fluids. Here are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.